Swayam Prabha. Digital India. Educated India.
In this lecture, we will be discussing how we can find the transfer function of the aircraft attitude dynamics. In this direction, we will be finding two different transfer functions. One is the angular displacement with respect to total torque or moment acting on the system. And another is the angular displacement with respect to the total disturbance acting on the system. From this transfer function, we will discuss then the concept of poles and zeros in the system from the transfer function. Then we'll move to the closed loop control system. In the closed loop control system, what are the different subsystems are connected in loop and how we can fulfill our mission objective. We'll discuss them briefly. In this lecture, we'll be talking on how we can design a control algorithm for an aircraft and how we can come up with the closed loop control system diagram where we'll be considering the disturbance and noise in the system and how we can mitigate over time. Let's go back to our previous lecture. The equation we had, the aircraft attitude motion in one axis, we had I theta double dot equal to m plus m this, or we can write md, m disturbance. Here theta is the angle we would like to control, m is the total control torque given by the controller, and m this is the disturbance coming from the environment. If you apply the Laplace transform, let me write this equation number 1, taking Laplace transform yields I s squared theta of s equal to ms plus md s. In terms of control variable y of t and u of t, if you write in this in that form, we can write in terms of y of s equal to theta of s and u of s equal to ms. Then equation this, let's write this equation number 2. Here initial condition assumed to be 0, so we have assumed the other initial condition is 0. So now equation 4 we can write, equation 2 we can write yields ys equal to 1 upon I s square us plus mds. And as you know, the transfer function basically relates between the input and output, and also transfer function generally defined for CISO system. Transfer function are defined for CISO system and single output system. But if you notice this equation number 3, there is 2 inputs us and mds, but 1 output ys. But if you look, they are actually acting separately. We can say us coming from the controller and MDS coming from the disturbance, I mean part of external partitions maybe. Now, if you write the ratio, the G is basically the transfer function if you denote, and Y is how Y is going to reflect it with respect to US when MD is equal to 0. So this is basically the relation between the output and input when one other input is 0. So now again we can write OIS divided by MDS when input which is given by the controller is 0. So in that case we can write IS square. So in both the cases, if you notice, the transfer function remain to be same. So GS equal to 1 upon I s square. So for both the cases, it remains same. So now we can write, since there is two inputs, we actually have two plant transfer function, but they are same actually. One from the control input to the output, and the other from the disturbance to output. So we can write, we have two input, one from controller to output, and another one is another one from disturbance to output. So you can see that equation, for equation 2 and 3 are same for both the cases. Hence, we can write I is equal to GS US plus MDS. So here, this is the basic transfer function for this particular system. But if you have any general system, for example, any other LTI system, and we are having one input and one output, for general, so this is what I'm going to do is the concept of pole and zero. For LTI system, we can write the transfer function, we can write G of S equal to A naught Sm plus A1S A minus 1 dot plus A. And we have polynomial for the denominator Sn plus B1S in minus 1 plus dot plus Bn. One more thing here, actually, if the system is proper, always, let's remember, m should be less than equal to n. It means the polynomial degree for denominator should be higher or equal than the polynomial degree in numerator. Let me write this equation number 4. Here, AI and BI are the real coefficients of GS. And which can be this equation? The equation 4 can be factored into, we can write G of S equal to K sum gain some constant for the time being. Let's assume it. M I equal to 1 S minus Z I divided by summation, sorry, it's multiplication basically, 1 N S minus Pi. So here Zi, I mean, we can write this polynomial, numerator polynomial, we can factor in this form, and the denominator polynomial we can factor in this form. So that basically from this concept we'll be coming up the concept on pole and zero. So here Zi are the roots of a naught s to the m plus a1 is m minus 1 plus dot 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 plus m equal to 0, and which are called, actually these roots are called the zeros of Zs, and Pi are the roots of Sn plus B1 is n minus 1 dot 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 plus Bn equal to 0, and these roots are called the poles of Gs. Now let's design the feedback control system for the above attitude dynamics. So now let's design feedback control system for the attitude motion. Why feedback? Because if you consider we have controller, let's assume GC with the controller which will be giving the input to the plant u of t, to the transfer function gp for plant gps, and this is my output y of t, which is nothing but theta of t. But if you want to track your y of t to some desired y dt, for example theta desired t, some desired angles, so how will make y of t equal to theta of t or y dt? So for that we need to come up with some kind of form of error. We need to come up with some form of error, which is y d minus y. It should be, as time proceeds, it should go to 0. So it means when it goes to 0, y desired to yt. So this is how we can design the control system. But in the open loop structure, we can't come up with the error function, because the output variable should be available at the controller so that I can find the error. But in this open loop transfer function, it's not possible. So we need to consider the feedback control system where we'll have sensor on board, and sensor will measure the current value of the attitude, and this current value will go to the some kind of summing point where we'll find the error, and that error will going to the controller, and controller will provide the necessary control torque to the system. Yeah, so this is how we'll be that's how we need to design the feedback control system. So here our plant is y of s equal to gp of s u of s plus mds. So this is our system, and for this system we will be designing controller. So our mission objective is Mission objective YT follow a reference or a desired signal. Let's denote R of T, which is, we can say, a desired attitude that we would like to maintain for the aircraft, theta d t, and the Laplace form of this, the Laplace transform of RT, we can write R of S theta d s. So this is what you would like to get. Our aircraft should follow this attitude angle with the application of control. So our contour, the contour input must correct error E of t equal to theta dt minus theta t, which is nothing but R of t, Y of t. Because y of theta of t we denoted as y of t, and theta dt we denoted as R of t. So objective is E of t tends to 0 as t tends to infinity. Since we are, as we said, that we need to come up with some, with this motivation, let's look the closed loop control system, which will provide the desired angle with the application of control. So now let's have a control block here, which will provide the desired torque to the system, GC of S, the controller transfer function, controller transfer function, and this is the output from this controller. Let's denote U of S, and there is also disturbance also in the system. So the disturbance to the system is MDS, and the sound is going to the plant GP of S, which is basically 1 upon I S square, the plant, and this is plus, and the output from this is Y of S. And let's assume we have onboard sensor on the aircraft who is sensing the current orientation of the body. This is my H of S. This is, we can say, sensor transfer function. And we are having desired output YD T, or we can say theta ds, or we can also write YDS in Laplace domain. This is the forward loop, and we are having the feedback from this sensor is going to this humming point. This is negative and this is positive. And from this block diagram, this is my error E of t, which is basically the difference between ys and yds, or I can say E of s. in Laplace domain. But in practically, due to the sensor measurement noise, so sometimes the signal we are getting from through the sensor is not perfect. So there can be noise in the system, in the measurement noise on the sensor. So we can have another summing point here, which is basically the entering the measurement noise to the system. Let's denote WS. So let me write here, what is this actually? For any real sensor, the measurement is not perfect. And this is corrupted by the noise WT, Laplace of WT, you can write WS. So hence, the sensor does not provide the actual output YT. Instead, it provides YT plus omega t. So this is actually the feedback signal going to this summing point. So if I say this is my Y of S, so this is plus, this is also plus. So at this terminal, the input to the summing block is basically YS plus WS. So hence, the error signal goes to the controller part. We can say E of t equal to R of t minus Y of t plus omega of t. This is the error signal actually goes to the system, the controller block, not the actual Y of t or Y of S. This is the most critical situation we can handle. I mean, it is more practical actually. In practical also, there are error in the system, in the measurements. So I can say this is not the true error. True error, which is basically Y of t equal to Y dt minus Y of t, or R of t minus Y of t. So, but instead of this, we are actually, in practically, we are giving this error signal to the plant or to the controller. So now, here, one more assumption we have to consider here, another assumption. In figure 1, that the sensor transfer function h of s we are assumed to be 1. For the time being, we are assuming the sensor transfer function is 1. So once the h is equal to, when h is equal to 1, we call this kind of system, we call unity feedback system. Because if it is h is equal to 1 here, then it is just straight line. There is no transfer function in the loop. So we can say this unit feedback, just feedback. And also, if you noticed from figure 1, it's noticed that there are three the external inputs to the system. And these are, one is reference input, which is nothing but R of S. So if you see this block diagram, there is three different external inputs to the system. One is the desire, only the measurement noise, one is the disturbance, which are coming from the externally. So that's why one is reference input. Another one is, we can say, measurement noise, which is WS, and another one is the disturbance, which is MDS. But as per the transfer function concept, this is basically relates between the single input and single output. But we are having three inputs. So we need to calculate individually the effect of inputs on the output. So we need to find three different transfer functions from the system. One is y of s with respect to r of s, and y of s with respect to omega of s, and y of s with respect to md of s. And we will see how the response changes and with respect to the individual inputs. And since the system is linear, the combined effect on the output is just the sum of the individual effect. I hope this is clear to you. Individual effects. So we'll find three different transfer functions with respect to RS, WS, and MDS, and we'll just sum the effect, and we'll see how the system is going to behave. Let's stop it here. We'll continue from the next lecture. How we'll find the transfer function with respect to different inputs on the output, and we'll see the combined effect, how it is changing, the system is going to change, and how the controller going to be affected on the system. Also noise, also disturbance, we'll look separately. So let's stop it here. We'll continue from the next lecture.